Hello and Assalamualaikum. We are from Team 5 and my name is Muhammad Adam Adaham. At 22010279, we'll present to you our control system project on modeling and control of variable geometry actuation system for gas turbine. Now, let's continue for the introduction. Now let's see our introduction. Our project focuses on the modeling and control of the variable inlet guide vane or VIGV in the Siemens Energy SGT-800 gas turbine. The VIGV regulates the airflow entering the compressor and play an important role in maintaining compressor efficiency, surge margin, and overall turbine stability. The vane position is controlled using an electric servo actuator operating in an enclosed-loop feedback system. The main challenge in the control system is to present all the measurement noise from the angle sensor. Excessive noise can affect the playing angle tracking accuracy and cause unnecessary actuator movement. Although accuracy controller gain can improve the response speed, it may also amplify high-frequency noise and reduce robustness. Therefore, a control strategy is required to achieve accurate tracking while maintaining stability and noise rejection. The objective this project is develop a mathematical model of the VIGV's electric servo system, design like compensator, and validate the system using MATLAB and Simulink. The controller must satisfy the performance requirement of the maximum overshoot, less than 12%, 30 time less than 2.5 per second, and phase margin greater than 40 degree, and gain margin greater than 6 decibel lag. The lag compensator is selected because it improves low frequency tracking performance while limiting excessive application of high frequency sensor noise. This study focus on modeling the VIGV as a second-order electric servo actuator and evaluating the compensated system through the step response, load locus, and frequency domain analysis.
My name is Liwesh and today I'm going to present about chapter 2, which is the literature review. So there are three important aspects in this, which are background, dynamic modeling, and also controller selection. Let's talk about the background. So as you know, gas turbines are widely used in power generation and CHP plants due to high efficiency and flexible operation. The Team 5, which is our team system, focuses on the Siemens SGT 800 VIGV, which control compressors, inlet airflow, and improve stability during load changes. Second is the dynamic modeling. The VIGV model is modeled as the second order electro servo system. The model includes motor dynamics, vane angle output, angle sensor feedback, and also the measurement noise. This allows transient response and stability to be analyzed. And third is this selection of the controller. A lag compensator is selected because our team main constraint is measurement noise. It improves low frequency tracking accuracy while reducing high frequency noise amplification. On to the next slide, there are three parts to be considered about, which are gas turbine, dynamic model, and also controller design. Talking about gas turbine, the SGT-800 industrial gas turbine with variable inlet guide vanes for CSP applications. And also for the dynamic model, the second order transfer function representing the electro servo VIGVT actuator. And last but not least, which is the controller design. And as I mentioned in the previous slide, the lag compensator selected to improve tracking accuracy while reducing measurement noise effects.
Hello, good day everyone. So today I'm presenting chapter 3, modeling our electric servo system. Our goal is simple. We feed electricity and we want a precise mechanical angle out. So to describe this, we start with two basic physical laws. That's first Kirchhoff law, describe the electrical side, how voltage pushes current through the motor coils. Second is Newton law of rotation, to describe the mechanical side, how torque turns the motor shaft while battling heavy inertial friction. Now, raw physics give us calculus with time derivatives, which is very hard to solve directly. So we use tool called the Laplace transform. Think of it as a translator. It turns hard calculus into simple high school algebra by moving us from time domain to the frequency domain. So and then we combine both equations into one single formula called a transfer function, which is simply output divided by input. To keep our math clean without losing accuracy, we assume the car's electrical inductance LA is so tiny and it's negligible. Next, we plug in our actual physical numbers like coil resistance, motor torque, and inertia. So this gives us our final transfer function. As you can see, it's G as equals to 5 over S bracket S plus 10.25 bracket. Finally, we don't just guess, we simulate it. In MATLAB and Simulink, we feed a step input, which is like suddenly flipping the power switch on. We set a we set up a closed loop systems which acts like a driver keeping eyes on the road. It measures where the motor shaft actually is, compares it to where we want it to go, and checks how smooth the response is. I think that's all from me for this chapter 3. Thank you.
Hello, my name is Muhammad Amir bin Masakus, student ID 22010237. I will explain about the control design for the variable inlet guidance event or VIGV control system. Based on the project requirement, Team 5 was assigned a lag compensator. The planned transfer function delivered by person 1 was used as the basis for the controller design. The objective was to satisfy with the required performance, which are maximum overshoot of 12%, settling time of 2.5 seconds or lower, phase margin at least 40 degree, and gain margin at least 6 decibel. The general form of the lag capacitor is the C bracket S equal to K S plus Z over S plus P, where K is the controller gain, Z is the compensator for 0, and P is a compensator of pole. Controller parameter are determined through the iterative using MATLAB. Several combination of K, Z, and P value were valued to improve the system response while meeting the requirement from the assignment. After comparing the result, we have managed to obtain final controller is C bracket S equal to 6S plus 1 over S plus 0.6. This controller achieved an overshoot 7.595%, settling time of 2.447 seconds, phase margin of 66.82 degree, and infinite gain margin. Therefore, the controller managed to satisfy all the requirement specification for the project. Thank you.
So I'll be presenting on chapter 4. The objective was to evaluate whether the design lag compensator satisfies the required design and stability specification. And the system was assessed using step response, root locus, and board plot analysis, with emphasis on maintaining a good performance while reducing the effect of the measurement of noise. This slide shows the time domain performance of the compensated system. The design lag compensator achieved an overshoot of only 7.59%, which is well below the required limit of 12%. The settling time is 2.447 seconds, satisfying the design requirements of less than 2.5 seconds. Although the response is slightly slower than the uncompensated system, it is much more controlled and stable, making it suitable for accurate VIGV position control. The stability of the controller was verified using root locus and board plot analysis. From the root locus, you can see that all of the poles image in the left half of the plane, indicating that the closed loop system is stable. The compensator system achieved a phase margin of 66.82 degrees and an infinite gain margin, both exceeding the required specification. This result confirmed that the controller provides sufficient robustness while maintaining stability. So here you can see the compensator equation, and the design lag compensator successfully satisfies all the required performance specifications. It improves tracking performance while maintaining adequate stability margins. Since a lag compensator has limited high frequency gain, it also reduces sensitivity to measurement noise compared with lead or PID controllers. Overall, the proposed controller provides a stable and reliable and robust solution to the VIGV actuation system.
In conclusion, this project successfully modeled the Siemens Energy SGT-800 VIGV electric servo system using the transfer function we derived. Unlike compensator we obtained, was then designed to improve the system performance. The final controller achieved an overshoot of 7.595%, 13 time of 2.447 second, phase margin of 66 degree, and infinite gain margin, satisfying all project requirements. Root locus and boot module analysis also confirm that the system is stable and robust. Therefore, the proposed controller provides the accurate VIGV position control while maintaining the good noise handling capability. For future work, several improvements are recommended. First, the model can be enhanced by including nonlinear effects such as actuator saturation, backlash, friction, and dead zone behavior. Second, a more realistic measurement noise model should be considered, including sensor bias, drift, and delay. Robustness testing under parameter variation should also be included to evaluate performance under uncertainty. In addition, increasing the controller gain from 6 to 7 may improve the settling time margin. Finally, hardware in the loop or experimental validation is recommended to verify the performance under real operating conditions.